suis ravi de parler devant ce public. Je reconnais plusieurs visages, d'autres je ne connais pas, mais je vais vous présenter mes travaux en optimisation de boîte noire. Je vais faire en anglais. On m'a demandé de le faire en anglais. Fait. Black box optimization is the subject of my talk today. So, brief overview of the talk. What's black box optimization? Explain to you the general context. Then move on with some methods that are designed to attack these types of problems, direct search methods. And in particular, I'm going to talk about the MADS algorithm using surrogate functions. And then I'll talk about our team here in Montreal and conclude. So, first part. What's black box optimization? Well, we're in the game in which we want to optimize some function. We want to find the minimum value of some function f, subject to some constraint. The vector variable x has to belong to some domain called omega. And the difficulty in that kind of optimization problem is that in order to compute f of x and to compute the constraints that define the set omega, we need to launch a computer code, a simulation that I call a black box, illustrated by black box over there. So it takes as input some x and then does some computation and tells us if the value of f of x and tells us if the constraints are satisfied or not. So that's a general framework for optimization, but we're in the particular case that has the following components. So x can be a vector of continuous, granular, or discrete variable, or a mixture of all of that. The game we're playing is that since this is designed mainly for real applications, computing f of x can be expensive, can be time consuming. So there's an example in valve train design where each time you compute f of x, it's a question of seconds. In work that I've done, one of my students have done a few years ago in spent potliner treatment. This was done with Jamal Shawki was the co-advisor of this project. Each evaluation costed a few minutes to compute one time f of x. With Dominique Urban, we worked on parameter tuning. Every time we want to assess the quality of an x, it took a few hours. That's quite long. So you want to optimize, find the best x, but every time you compute it, takes 3 hours to compute. So that's costly. And the worst we've seen was someone that was doing her PhD in Stanford. Each evaluation required 2 weeks of CPU on a network of computer. So she was in mechanical engineering and she was told to optimize to reduce the trailing edge noise at the rear of the wing. She was given 9 months of CPU. So she figured out she had 20 calls to the simulation, 20. So she looked into literature, she contacted us, and she worked to optimize this thing. And she reduced the noise by 90% by applying some optimization techniques. And this is what I'm going to talk to you about, the type of techniques we developed to attack these problems. So time is consuming. Another problem is that the simulation does not always work. So you give it an X, it crunches a number, and then it crashes. It returns an error. And you don't know what error. It's error number 42, and you lost the manual what error 42 means. There was a problem at Boeing in helicopter rotor blade design, where 60% of the time, the code produced by the engineer failed to return a value, which is not that surprising because when they conceive the code, they conceive it to have it in nice working condition. The variable must satisfy some reasonable condition to be, and they don't tell us the constraint that tells us that these are the reasonable condition. And optimization, what it does is it tries to find the best solution. So it pokes around in the space of variable to find good configuration, and it explores some regions that are banned by the the problem itself, leading to errors. So 60% of failure is not surprising in some situations. Sometimes when you compute f of x twice with the same x, you don't get the same value. So if there's some stochasticity or randomness inside the black box, you feed it x, it throws a Monte Carlo simulation and returns a different value. So technically, it's not even a function. In math, we like to work with functions, but this is not even a function. For all these reasons, derivatives often do not exist. So you look at the function f, objective function, or the constraint, they look like the thing you don't really see at the right. It's a function that's discontinuous at many places, and derivatives simply don't exist. Or when it's real noisy, if you do a finite difference scheme to approximate it, you might get some horrible results. So discontinuity is another type of difficulty. Here's an analogy of what we're doing when we're trying to minimize such functions. I like the analogy of John Dennis. He said, well, your minimization problem is to find the deepest place in a lake. And the only tool you have to measure the depth at a point is you go in your boat and you take this line with a stone at the bottom and you measure the depth there. So how do you minimize to find the deepest place in the lake is if that is your only tool? You don't have gradient information. So gradient information tells you that if you want to go uphill, you go over that direction and downhill will be the opposite direction. If you don't have a gradient, it's like this way at the end of the rope. You just measure there and you don't have more information. So that's the kind of problems we're dealing with. And these discontinuities and these difficulties are both for f, the objective function, and for the constraint that define the domain. So that's black box optimization. That's the target problems that we have. And we study these problems because the industry faces such difficulty. So I'll just try to. Okay, so few definitions. Black box optimization refers to problems where the structure of the objective and constraint function cannot be exploited. Often it's because it's too complicated to be exploitable. In some situation, it was because of confidentiality agreements. I did some work with Exxon Mobil at some point, and the only information they gave me that it was for petroleum. That's it. I don't know if it was finding the petroleum, digging, putting wells, transporting it, whatever. It was petroleum. That was my insight. And I had to solve some optimization problem with them. And they financed me a while because they liked what we did. So it's a real black box. And often the information within the black box is not available. There's another term that's quite related. It's derivative-free optimization. This refers to situations where you still don't have access to the explicit derivatives, but you suspect that the model is smooth and derivatives exist. So in derivative optimization, you don't have the analytical value of derivatives, but you expect that if you build models, if you try to estimate what functions look like, it will be useful. The models you'll build will help guide you toward an optimal solution. So these are two words that are frequently used. So my research here. In the center, I worked on black box derivative-free optimization. And for me, there's three pillars. This research lies on three aspects. First of all, applications. I deal with industrials, I deal with real optimization problems, and I see what they want to solve. In order to solve that, I develop some algorithms, some methods that are adapted to solve them. And I'm not in the game of heuristics. I'm not developing genetic algorithms and running them once or twice, saying it's good, and then moving on to something else. I want to make sure that the algorithms that I develop are supported by convergence theory. So I do some math to prove what the algorithms will produce, to get some guarantees of the quality of the solution at the end. So a few examples. This was a project I worked on in 2004. So this was after the big tsunami that hit the Indian Ocean. I don't know if you remember, but there were 250,000 deceased. So it was huge. So with the tsunami, it's a big wave that's either provoked by an underwater volcano or underwater earthquake. And then big waves come, hits the shore. So what can you do when a tsunami comes? Nothing. It's so huge. There's nothing you can do except run. Run for safety. So in the US, when they saw what happened in the Indian Ocean, they decided that they would put some tsunami buoys on the Pacific Ocean to detect potential tsunami waves. So they did all the technology, all the engineering behind that. So essentially, they have buoys that floats. They're connected to the ground by a 6-kilometer chain. So it's quite deep, the Pacific. And at the bottom of the ocean, they have some sensors. So the sensors, what they do is they detect the vibrations on the ground. So if over here, an earthquake or a volcano starts to activate, the ground will shake. The sensor will detect it, will tell it to the buoy will tell it to the satellite, and the satellite will tell it to the control center in Seattle. So if you have enough buoys, you can do some triangulation and determine the origin of the earthquake, the strength of the earthquake. You can build a model of the wave that it will create, and you can propagate the wave and tell the cities that, hey, a wave is coming in a few minutes or an hour, etc. So they did all this technology, and then they came to a point where they said, okay, where should we deploy these buoys? They had, I don't remember, I think it was around 50 buoys that they wanted to put in the ocean. Where do you put them? What's the best place to put buoys? As soon as you hear the word best, that means it's an optimization problem. You want to find the best solution according to some criteria. They had no clue of how to define what would be a best position. So they looked into literature and they found John Dennis, which was actually living in Seattle at the time, and they contacted him and they invited him to work on that project to define what is meant by the best position. And then the second question, how to find that best solution. So this is where I was involved in that project. So what do you want to optimize here when you put the buoys? What's the thing we want to maximize or minimize? Well, since there's nothing you can do beside running in front of a wave, we want to maximize the warning time. So if you call and you say, San Francisco, there's a wave in 42 minutes. And if you call and you say there's a wave in 37 minutes, there's a big difference. 5 minutes saves a lot of lives and material and hundreds of thousands and millions of dollars. So the question was where to put the position these buoys to maximize the probable warning time to populated cities on the Pacific. So we model all of that. So this simulation to compute all of that generates some earthquakes and then generates a wave, looks at the deployment time, at the way the wave is deployed, see when it intercepts the buoys, computes the warning time, etc. So that was the black box. Well, that's an example of black box optimization problem that our methods are able to address. So we adapted our code, we installed them on their machines, we did some tests with them, and at some point we weren't involved because I don't need to know where are the buoys. They did the test by themselves, and as of now, the buoys are deployed in the Pacific. So that's an example of a problem. Another problem that's interesting is Photon Surgery. So this is a surgery that's done on newborns. So baby born arrives, and he has a heart defect. Actually, a defect in the valve that's above the heart that's over here. So what the doctors need to do is to cut part of that valve and replace it by a plastic one. So I'm sure you're more knowledgeable of me on what type of material would be used and things like that. But the optimization problem is, what's the best shape that we should put for that individual baby? So what's the optimization problem? What do we want to maximize or minimize here? So baby, when it's born, it's this big. In a year, it will be this big, and 2 years, so it grows quite rapidly. So the valve that you will put in will soon become obsolete, and you'll need to put another one. This is no minor surgery. So you want to delay as much as possible the next operation. So the optimization problem here was to maximize the time, the expected time before the next surgery, subject to that the valve fits correctly the baby's morphology. So that's another example of an optimization problem that we're looking at, involving simulation, of course. Hyperparameter optimization. This is very sexy these days. So you build a network, a neural network, and you optimize that network so that it recognizes faces or dogs or cats or things like that. So when you optimize that network, you solve these huge optimization problems with other methods that are dedicated for doing that. But when you design your network, you need to take some decisions. How many layers will you put in your network? How many nodes will you put in each network? What kind of activation function will you use in your network? These are hyperparameters, and there's not a ton of them. So it's compatible with black box optimization, where your variable are define the structure of your network. And in order to assess the quality of these parameters, you need to train a neural network. So that's a subject that's that's used a lot these days. So these are the kind of examples that we're looking at. And when looking at application and looking at particular problem, we devise algorithms that exploit a bit some of the structure of the problem. So for example, in the tsunami problem, even though it was a black box, we knew that the variables represented pair of coordinates for each of the buoys. So there was a bit of knowledge that we could use. So in our algorithm, we exploit that fact, that the variables are not just spread out like anything, they come in pairs. So we use some information when we can to devise algorithm. We've got algorithm, we want to analyze them. So there's no derivatives. So we cannot use gradients. They just don't exist. So we need to use generalized tools. So there's something called generalized gradient and generalized derivatives that looks like the expression on the right. This is a directional derivative, but it's not as simple as the one you learned in the basic calculus. So there's a limit superior, and there are a bunch of things that are moving around. We want these directional derivatives to be non-negative when we have direction that point inside the domain. So that means that when you move toward the inside of the domain, you want the objective function to increase if you want to get a minimizer. So these are the kind of tools we use to analyze our method. Theory and application, when we apply it to some problems, we want to make sure that it's compatible with the theory, and some application allow us to devise some new ideas for the theory. For example, the hidden constraints, the constraints I've talked about before, where you evaluate your function and it fails, it crashes. Well, it's a fact. It happens in real life. Can you still do some nice, rigorous theory with that? Well, we do. We have some tools that allow to deal with some such comportment. So that's the class of problem we're looking at. What type of algorithms can we use for that? There's not a ton of them. There are some direct search methods. These direct search methods, they work directly and uniquely with the output of the black box. So we feed X and returns f of X. That's it. So direct search is direct in that sense. There's another approach that's very useful sometimes is to use surrogate functions. So surrogate function is an approximation of the truth. It's a light version of the problem you want to look at. So if you use some discretization on a fine mesh to model your problem, if you use a coarser mesh, it will run faster and it will be an approximation. So surrogate functions can be real useful in optimization, and hybrid methods are essentially what me and my team are working on, are direct search methods that recalibrate and model models and surrogates. Okay, so let's talk a bit more about the type of constraints that we're dealing with. So abstractly, the domain is omega. So I write this set of X in capital X such that a bunch of constraints Cj are satisfied, Cj of X is less than 0. And we're in Rn, we have finite dimensional problems. Typically we have a small number of variables. The rule of thumb that we give to our users is if you model your problem with more than 50 variables, then we're a bit scared and maybe we won't be able to solve it. If you have hundreds of variables, you need some parallel infrastructure to hope to solve your problem. So many of the problems we're looking at have maybe 10 or 20 variables, are small scale, but the difficulty is in the computation of the functions itself. So omega is a set of little x in capital X. These are the unrelaxable constraints. They cannot be violated in order for the simulation to run. So for example, one variable is one length. Well, if it's negative and you feed it to the black box, it will stop. It will say, no, I won't compute anything because it's negative. So these are constraints that are not relaxable, that are often known a priori. The other types of constraints are the ones that are relaxable. So we can quantify them. We can put a number of them on them, and it's not because it's violated that the output of the simulation is wrong. So an example is that we had a constraint that tells us that the thing we're building has to be within the budget of $1,000. Well, you run your simulation and your thing costs $105. Well, okay, that constraint is violated, yeah, but all the information that the black box produce can be used to build models and to guide the optimization further on. So relaxable constraints are constraints that can be violated, and that means that the optimization method that we'll develop will allow to move in the infeasible part of the domain to reach better solutions. So that's useful for us. Hidden constraints are the nasty ones, the one you did not expect. It crashes, segmentation fault, bus error, etc. So, and in a lot of engineering-made black boxes, there are some hidden constraints like that. They pop up all the time. So the optimization method needs to be robust to that. So back to the spin potliner treatment problem. Aspen, the Aspen software was used to model this treatment. And if you look at the graph on the right, we fixed all variables but 2. And we put a grid just to see what the objective function looked like. So the floor, on the floor of the graph, the blue part on the graph is the places where the simulation crashed. So it's that. And if you look at the ceiling of the graph, when it's red, these are places where the constraints were not satisfied. So the game here is to minimize that function, staying away from the ceiling and the bottom of the graph. And this is only for 2 variables. So these problems we're looking at are quite difficult. What about the variables? Well, they can be continuous, they can be integer, or they can be binary, they can be granular, so they can take just a finite number of values. They can be categorical also. So back to the hyperparameter problem. So this is a neural network with many layers. The activation function, for example, it can be a sigmoid, an hyperbolic tangent, or a relu, for example. So these are examples of activation function. So we can model them as 1, 2, 3, but actually there's no order between them. 1 is not closer to 2 than to 3. So categorical variables are difficult because there's no notion of distance associated to them. But still, many optimization problems have these kinds of variables. Another variable that's kind of tricky is the number of layers. So if you add a layer in your graph, well, you will need to decide how many nodes you'll put into them. And you'll need to find out the parameters of this node. So the actual dimension of the optimization problem is an optimization variable. So that's quite difficult. Nomad, the code we're working on, allows us to use these kind of neighborhoods. Okay, so what's black box optimization? That's black box optimization. These are the problems we're looking at, and we're looking at them mostly to be able to solve real applied optimization problems. So how do we do so? Let's talk about direct search methods. Direct search method is simplistic in the way we can present it. We've got our algorithm on the bottom. It gives an X to the black box. Black box compute F and tells us if it's feasible or not. And then the algorithm finds another candidate X. So it turns like this. At some point, it stops and suggests a good solution. So the way that the algorithm finds which will be the next X is what defines the algorithm itself. So let's go back to 1952 with Fermi and Metropolis. They proposed the coordinate search algorithm and used it on the Maniac computer. And you have a nice picture here of Metropolis in front. I really like that picture. So how does coordinate search work in the 1952 version? Let's illustrate it on a problem with only 2 variables, but the generalizing to n variable is quite direct. So you've got a best candidate. X1, X2 is the central dot here. So that's the solution you want to beat. No constraints here, unconstrained problem. So what the coordinate search algorithm puts a grid on the space of variable. So it will consider the 4 neighboring points, the 4 red points. Will increase each variable by a fixed amount, increase or decrease, and it will sample these 4 points in hopes of finding a better point than the current one. If there were 3 variables, there would be 6 neighbors. If there were n variables, there would be 2n variables. So that's good. It's not 2 to the power n, it's 2 times n. So it's linear, so it scales relatively well. So you look at the neighboring point. If all the red points are worse than the central one, so Fermi and Metropolis, they said, well, let's reduce the step length and do the same thing. So if your central point is better than the neighbor, it's kind of a suggestion that it's a good point you want to minimize, and your objective function value is smaller than the neighboring one. So you failed to produce a better point, but it's a good thing because it suggests that it satisfies some rough minimality criteria. So you do the same on a smaller mesh. If it turns out that the point to the right is better than the central one, well, you will move to that point and continue the algorithm from there. That's it. So you can write this code in MATLAB in a few lines, and you'll get a coordinate search algorithm. So in the 60s, Hook and Jeeves came up with the term pattern search to propose another type of method. And in 97, Torkson proposed the generalized pattern search algorithm, which generalizes the Fermi metropolis, generalized the pattern search, and a few other algorithms. And it's essentially the same idea as coordinate search, except that instead of only looking at the neighboring solution on the coordinate grid, you're allowed to twist your grid and look at diagonals. So you can use these 4 points at one iteration. And when you have a success, you allow to take larger step, you expand the grid. So that means that if you have a success, you can take larger and larger step and adapt to the fact that you're decreasing. And it also, so you can change a set of directions from one iteration to another. And it also allows the user to bring in part of his knowledge to help the optimization. Why? Well, at the time of that research, so Torkson was a student of John Dennis at the time, and John worked a lot with people at Boeing, and he was working on these methods, and he took his code, brought them at Boeing, gave it to the engineer over there, and they used it to try it out to see how it goes. And at some point, the results were awful. The results of the codes were not optimizing anything. They were performing very badly. So John asked them, well, why? Did you do something to the code? So the engineer said, yeah, we improved it. So what they did is that they put part of their knowledge to try to explore in some way, and thus breaking the nice structure of the convergence structure of the method. So John understood that the engineer had a better knowledge of the problem than he did. So instead of saying, no, you destroyed the code, you're no good, he said, okay, you've got good ideas, but let's split the algorithm in two phases. One global search phase and one local poll phase. So the local poll phase is the one in red, is the one I'm talking about. This is what ensures that we converge to solutions that satisfy some optimality criteria. And in the other phase, we told the engineer that they could add their expertise. They can add any type of exploration they want, as long as they satisfy some minor conditions. And this is what became the generalized pattern search method. It's a method that iterates between the global phase from the engineer, the local phase to ensure convergence, and it cycles between them. So that's pattern search in 97. So essentially, every time the algorithm proposes an X, it's either from the search or from the poll step. Okay. So I need to do a bit of math because I'm a mathematician. So that algorithm, as simple as it might seem, you just look at neighboring point, and when you have a success, you move to it. Otherwise, you refine the grid and you continue. This algorithm, as simple as it is, allows us to prove some convergence results. And convergence results depend on the smoothness of the function. If your function is differentiable C1 or C2, the gradient exists, well, this guarantees that you'll converge to a point where the gradient is 0. So that's reassuring, but it's not our target problems. They're not smooth, they're not nice. So it's reassuring that we get this result, but it's not useful for us. If the function is only Lipschitz continuous, well, we have that the generalized derivative that I talk about will be non-negative for every direction that's used infinitely often. So if we look at the coordinate directions, let's say we always use the north, south, east, west directions. We converge to a point where, at that point, if we look north, the directional derivative will be positive or not. Same thing if we look south, east or west. In all directions that we look, the function looks like it's increasing. So that's another condition, necessary condition for optimality. So we can guarantee that. Replace the word directional derivative by generalized directional derivative, and that's what we do. Okay, so I have 2 elements in the hierarchy, but we have much more. I'll come back to it later. So these are basically direct search methods. If I talk about MADS now, the MADS algorithm dates from 2006. Don't worry about reading everything here. It's not that important. The only point I want to make is that initialization, to start the method, we only need a starting point. That's it. And then we fix a step size at the beginning. We update some parameter at each iteration. We do a search. So the user does whatever he wants. He can use a genetic algorithm if he wants. He does anything he wants with his expertise to optimize the problem. And then we go on to the poll step, which looks locally around the point. And then it checks for termination. So the algorithm itself is not more technical than that. I'll illustrate it by this graph. So these are level sets of F. I want to minimize that function. The starting point is the yellow dot here. So what I do, this is my grid. So in coordinate search and in pattern search, we use some fixed points on the grid. Here in MADS, what we'll do is we'll randomly, I'm spinning some direction, and then at some point I will stop. So I choose randomly these 4 neighboring directions. I evaluate F at those points. If there's a better point, I take it and I move from there. So the point here is better than the yellow one. So I'll move the next step will be starting here. So I go here. I coarsen the grid to allow larger steps. And I do again the spinning thing to generate some direction inside that grid. So I spin. It generated some functions. I evaluated F at those points. They weren't good. So I will reduce the size of the grid. And again, I will spin. I will generate some new directions here. And so evaluate F at all these green points. They're no good. So I will again reduce the size. But there's an important element that you will see here. If you look at the gray box, it's a 4x4 square. When I will reduce the grid, look at the smaller squares here. Instead of being 4x4, they're 8x8. So I have more directions to choose from. When I spin here, I have more candidates to choose from. Why is this important? Well, that means that as the algorithm unfolds and converges toward a point and starts reducing, there will be more and more directions for which I will be able to look at. So when I had the convergence result on the previous slide, I said, in coordinate search, I only knew that the directional derivatives were non-negative, northeast, southwest, in 4 directions. That's not a good result. I would have liked to say that all the directional derivatives in all directions are non-negative. And MADS allows us to do that specifically because of this thing of refining more aggressively when we have a failure. So, and then it continues like that. It turns, finds some point, and eventually it will find a good solution. So that's essentially the poll step of the MADS algorithm. So spinning these directions in Rn is easy. We have ways to do that. We just need to write adequate matrices and doing the math. It's not, technically, it's not that difficult. And again, that's the local exploration. This is combined with a global exploration that can help improve the method. Okay, surrogates now. Surrogates are a simplified version of the problems. How can we use them in an optimization problem? Well, this is where the surrogate fits in. So the algorithm can either call the black box, let's say it takes 3 hours to compute, or it can call the surrogate that takes 3 seconds to compute. So the surrogate can be used to get some information about some points before trying out the real black box. And at some point, we can recalibrate the surrogate to make it closer to the true function. So here's an example of that. So I've sampled the function at the blue points. I build a model using the blue points. So using the blue points there, I can fit this quadratic. The way I fit the quadratic is something else. So I build a quadratic model of it. So the level set of the quadratics are above in blue. Minimizing a quadratic function is quite easy compared to minimizing my black box. So I can minimize that quadratic and find the green point central here. And I can evaluate the real function at the blue point. So I can spend some effort working on the surrogate function to get some good candidate points. So that's one use of surrogate function. It can be used in many other ways in black box optimization, but I don't have time to discuss them here. So dynamic surrogates, there's a bunch of them. We can do some kriging, Gaussian processes, RBF, different types of quadratic approximation. The point is that they're cheap to construct compared to the black box. They're cheap to update and solve when the number of variables is small. So if I look at a graph like the one to the right, well, fitting a fine model on that is not useful. If I want to really reproduce that function, well, it's quite a messy function, so it's not good. But say you sample the function 3 times. So one time here, one time there, and one time there. And you fit a quadratic with those 3 points. Well, you'll be quite close to that blue thing. So building models on a coarse scale can help you to find the promising basins, the promising regions where the optimizer is. So even if the problem is nasty like that, building models might be useful. So these are dynamic surrogates. Static surrogates are the one that the engineer gives us. So he has a model, he used simplified physics elements to make like friction or thing, and you get a simpler version of the problem. You have a discretization. Well, you don't see it well, but there's a fine discretization on the left. You use a coarser model on the right. It will be much faster, and you can use it to guide the optimization. So you can use a Euler instead of Navier-Stokes. You can use a Monte Carlo with fewer points, etc. There are different ways of building surrogates, and these are crucial to improving the performance of an optimization algorithm because surrogates are used at many places. And bonus, it's not required that the surrogate is an approximation of F. So that is why they chose the term surrogate rather than model. A surrogate does not need to be a model. So for example, we had a situation where F, the objective function value that we wanted to minimize, was the time to perform 1,000 tasks. So we want to find the parameters so that the tasks are done rapidly. So if I do the task, it took us 3 hours and a half. So a surrogate is to take 5 tasks, not the difficult one, but 5 tasks, and to compute the time it takes to perform these 5 tasks. Well, if they're representative or not, well, they will give us an idea of which solutions are preferable to other. So when comparing 2 solutions with the surrogate, it might help us to order these ones before launching the real black box. So that's an example, and the objective functions are quite different. So f of x is 3 hours in one case, and f of x, the value is 3 minutes in the other. Okay, so the convergence analysis I was mentioning, I said a few words on the pattern search. On MADS, here's the whole hierarchy. I won't go into the technical detail because it's quite technical. I just want to show you that, to convince you that our methods rely on rigorous mathematical grounds. So under the assumptions that the iterates that we generate are bounded, well, we converge to a solution that satisfies this property. It's the minimum. It's the limit of minimum on meshes. So when you look north, south, east, west, the central point was minimum with respect to the neighboring point. And then you refine the grid, you got another minimum, you refined another minimum. So it's the limit of these minimums. This is what it says on the right. If it's lower semi-continuous, then f at the limit point is less than f at the sequence of fk. If it's directionally Lipschitz, then we get that the Rockefeller derivatives are non-negative for all direction. If it's Lipschitz, etc., we've got even more. If it's regular, we've got this. At the very end, we have KKT. If it's strictly differentiable, we've got that the gradient is 0. And strictly differentiable is weaker than differentiable. So it's even stronger than what a lot of other methods do. And we've got variants of these for constraints. I won't go into the details, but we've got similar results when we have constraints. Okay, so here's the take-home slide of the presentation. This is what I want you to remember for this talk. See, if your optimization problem has known structure, such as the explicit derivative, my recommendation is use them. Use those derivatives, use the appropriate method, use IPOP, nitro, Lancelot, Minas, and thing. Don't use my code. Use one of them. It will go faster. If it has derivatives but are unknown, well, approximate them using derivative-free methods. There's a few of them. I could have added here Nomad with adding the option to build models. And if it has none of the above, it's a real black box and you don't know what's in it, well, nothing else works. Use black box optimization methods. Nomad is not the only one. There's a few others like implicit filtering and brute force optimization. These are methods. And the image I have is the image of the cover of the talk. Methods on the top, they're lightning fast because they exploit the structure of the problem. They're a racehorse. Nomad, if you run Nomad on a linear program, it's a plow horse. It will get the good solution, but it will take forever to run. But if you try to take the racehorse and do the work of the plow horse, it won't be able to do anything. It will get stuck because these problems are too difficult for these problems. So my recommendation is use the appropriate optimization method depending on the nature of your problem. So who are we? Here's the snapshot of the black box optimization team. Christophe here is there. He's behind Nomad, he's coding Nomad. So this is just to show you that we're active. There's 3 professors in math that are working in that area. There's me, Sébastien Letizabel, and Youssef Diwan. Youssef got here last year. And we've got some postdoc research associate students, and a lot of people are working with us here. So a few words about Nomad. So Nomad is the implementation of MADS with all the bells and whistles that we've developed over the years. It's in continuous development since 2001. So we had a first research associate that worked on it, a second, and then we have Christophe that's been here for a few years. So it's a code that's quite mature. And in continuous development, that means that we have one full-time programmer on it since 2001. So it's an implementation of MADS. It's written C++. There are interfaces with MATLAB and Python and maybe some others that I don't. Java, okay, with some quotes around it. It's LGPL free license, open source. That means you can download it and look at the code and do whatever you want to with it, except sell it behind our back. So basically that's what the LGPL license says. There's a user guide with it, installation guide and everything. It works for a parallel environment, which is very nice because a lot of these problems, well, our clients have huge servers. At Hydro-Québec, for example, they have 5,000 nodes, I think, on their cluster. So we need to be able to handle that. It handles different kinds of variables, handle constraints, which is a big thing. So before 2006, no one was able to deal with constraints on these problems. So there's been a first development in 2006, another big one in 2009, and a lot of publication these days are on Blackbox or DFO problems, and they propose algorithm for unconstrained optimization. So they have new ideas, but they're not able to deal with constraints. So dealing with constraints is extremely difficult and important. We've got tools for bi-objective optimization. I talked about the generic search that the user can apply. We've got some variable neighborhood search and Nelder-Mead search that put some diversification into the method. It handles surrogates and models, either fixed surrogates or dynamic models. Its features are backed by published papers. And this line is important. Applied to real engineering problem, for me, it's important. Some papers and some methods are proposed and they don't even have an implementation and they say they have a good algorithm. Well, in theory, maybe, but having passed the test of solving a real problem is quite difficult. Okay. We've got essentially roughly 13,000 downloads, certified downloads. That means that people put their name and contact information when they do it. So that's roughly 3 a day. A lot of industries have downloaded it. The one in red are those that give us money these days. So we're working with Hydro-Québec, Huawei, and Rio Tinto, but that thing is finished. There was one I thought was funny. Disney Research. I have no clue what they're doing in optimization, but I would like to know. So, it's used by the national labs, Argonne, Berkeley, Los Alamos, Sandia, and universities throughout the world. So before ending the talk, I just want to mention a few projects that my students are working on. So Edouard is working on meta variables and machine learning. So when I mentioned the hyperparameter optimization, that's a difficult optimization problem, and there's a big demand for this these days. So how can you deal with such variables that have a nasty behavior? Different types of variables, some are categorical, some determine the number of variables. Depending on the value that they take, they might introduce new constraints, etc. So Edouard is proposing a framework, a unified framework to deal with such problems. And he's doing his PhD with us. Xavier, he's working in multi-fidelity constrained black box optimization. So this is joint work with Hydro-Québec, motivated from one of their problems. So the constraint functions are sequential. So you have 10 constraints to satisfy. The first one takes a minute, the next one takes an hour, the other one takes a day, and more and more costly to compute. So we want to break the flow of constraints when we detect that it's infeasible. And we've got another lever that can give us cheaper versions of the constraints. So constraint that will run faster, but will not give a good approximation, surrogates of these constraints. So how to play with those levers in order to solve the problem. So this is a very, very important problem at IREC, and we're starting to work on that. So there's a good potential for research here. Paul Patience, who's working with Bruno Blais, who's just over there. He's working on applying additive manufacturing to aluminum tool part design. It's joint work with NRC. So he's looking at the optimization problem, but modeling it from a different perspective to introduce some black box approaches in a domain where black box approaches were not used. So he's proposing a new ways of modeling things. And to do that, he needs to configure with various algorithmic tools. He's playing with a lot of software and is going to have a real application at the end. Pierre-Yves Boucher, he's in optimal control, where he partitioned the variables in two groups, some that have a black box nature and some that are continuous in nature, but very numerous. You have 100,000 of variables that are smooth. So he breaks the problems into two parts, kind of in similar to a bi-level kind of strategy, but the two levels agree on the direction they're working on. So he's working on optimal control with that. Romain Couder is working on a risk-averse optimization by Gaussian smoothing and CVAR. So he wants to look at robust solution. He has some risk assessment measures, and he's developing things like cross-entropy methods. So again, in Blackbox, but a lot of noise and stochasticity in that project. So, conclusion. DFO and Blackbox optimization are very active fields. When I started, so the late 90s in that domain, and I went to meetings, well, I was just about the only one talking about that. So I was mixed in some NLP session, and I was talking about this. There were one or two other people that were interested in that, but it was not a big thing. But now, every time I go to a meeting, there's a stream from day one to from Monday to Friday, consisting only on Blackbox and DFO method. So it caught on. There's a lot of people working on that. And that includes the big conferences, and I would like to do a bit of publicity for ISMP, which is the International Symposium on Math Programming, which will be held in Montreal in 2024. So it's the huge meeting in optimization, and it turns out that I'm the chair of that meeting, so that's why I'm doing some publicity. It's one of the branches of the journal Optimization in Engineering. So I don't know if you know that journal, if you published in it, but I think it's an interesting journal because when you submit a paper there are two editors that handle your paper. One editor from engineering and one editor from math. Both these editors find some referees, and you need to pass the test of all these referees and editors. So it's more difficult to publish there because of the extra referees, but you know that your paper will be read from the mathematical and from the engineering perspective. So that's a nice hybrid journal, I think. And one of their branches is Blackbox and DFO. And there was a special issue in 2016. So the first book on the subject came out in 2009, Introduction to DFO. And the second book came out in 2017. It's Warren Hare and me that wrote it. If I was able to go back in time, I would permute the titles of the two books because the second one is more an introduction. It's a course book. It's used in some classes. It's used here at Polytechnique. I give a course on that. It's used in other places too. The other one, the first book, is more intended to people doing research. So it's more technical, it's more difficult to read. If some of the students are interested in knowing more about DFO, well, take that course. And some of them did. Take that course and I'll talk about this during 13 weeks. There's enough material to go 13 weeks. So our research, how do we do research in applied math? Well, our research is always motivated by some real problems. We don't develop algorithms because we think it's nice to do so. We develop them so that they're applied at the end. So we listen to our partners, to engineers, to see which research direction we should take. And the algorithmic ideas that we have, well, I give it to my students and we work together with them. And often they involve real data from our partners. And I insist that the methods that we develop are supported by theoretical background, theoretical support. And because of that, we're able to publish in good journals. And once we've got our code written by the student and they work and they defend their thesis and everything is nice, we take all of that, we give it to Christophe, and when we feel that it's important enough to go in Nomad, and Christophe then does the implementation in Nomad. So Nomad is not a patchwork of 20 people that put some code in. We have a head coder that looks at every line in Nomad, or I hope he does. And yeah. Final slide. Future challenges and perspective. So AI is, everyone is talking about it these days. So there are ideas in artificial intelligence that could be used in DFO, and the converse is true also. There are some DFO like optimizing the hyperparameters that can be used in AI. So there's more things to do with these two communities. There's no dominant method. I talked a lot about MADS because it's my baby, but there are other methods that are quite good, and NOMAD is not always a champion. So there's no clear champion, and I really believe in hybrid strategies and stealing the good ideas from the others and vice versa to get better codes at the end. Difficulties that remain to be addressed. Escaping from local solution, that's always a difficulty. We've got some ideas on how to do that, but there's still a lot to do. Stochasticity, increase the size of problem, use of exploitation of parallelism, analytical expressions of some constraints, equality constraints in particular. Can we do something about that? Joint use of models and surrogates. And one other extremely important point, the last one, is when you guys work on an optimization problem, if you would be able to make a black box out of it, a code in language of your choice, and share it to the optimization community so we can test our method on them, it would be very helpful, because when I work with Rio Tinto or Exxon, they don't give me their code and their data. It runs on their server, on their machine. So my methods work great there, but I'm not able to reproduce and have the other researchers in the domain work on the same problem. So sharing black boxes is something that needs to be improved in my field. So you guys are in engineering, maybe you have some such problems. Sharing them would be quite useful for us. That's it for today.